cross products of vectors is also from physics. All of these operations in vectors are from physics because vectors were innovation from physics context, right? Newton invented them to describe the motion. And one of the things that you see in physics is the following. Torque is force times the distance, which is the distance from the pivot, times the angle theta. And it goes like this. If you have some pivot and you have something connected to it and you apply the force, let's say you're applying the force, this is your force, then this length here, from the pivot to the point where the force is applied to, this is called r, and this angle is called theta, and multiplying these two gives you a torque. And that can be used to find, for example, how much force do you need to balance this or counter this if you were to have another force from here pulling it up or something like that. If you are still taking Physics 1, you're going to be seeing this pretty soon. Okay? Let me show you another formula. There's something some students like to call it Bill the Science Guy. Bill the Science Guy. Bill the Science Guy. Have you ever seen this formula? What is this for? B is what? Magnetic field. And I is current. L is length of the wire. You multiply by sine theta, that gives you the force. So does that, oh, I see. A lot of you are taking Physics 2, right? Yeah. So you haven't seen this yet. Yeah. Some of you may have seen it, but in high school maybe, but most of you haven't seen it. You're going to see this pretty soon, okay? When you get to magnetic fields. Okay? Now, in these formulas, if you look at the formulas closely, then you see that these are not just formulas of scalars. These are formulas for vectors. Okay, so here's how people do it in this context. Magnetic field is definitely a vector. Current is flowing in a direction because the current is a vector. So these are vectors. L is a scalar, so that's just a multiple. And the outcome force, is that a vector or a scalar? Now, this quantity is scalar, I know, but as a physical quantity, force is a vector because force has a direction, right? Yeah, it's magnitude and direction. So these are actually vectors that we're talking about. So we have an operation where you take two vectors and it gives you a vector as an output. Let's look at this. Force is a vector. Lengths are not vectors, but you can still think of this r as a vector because you can think of this vector here. So it's a vector which begins at the pivot, ends at the point where force is applied. So that's this length r is the magnitude of this vector, and the direction that's the direction of this vector. Okay, so you can think of this as a vector, and torque is a vector. Okay. All right, going back, there's an important formula for the direction of this. It's called Faraday's law, right? It's is it this? Something like this, right? I used to know this.
Yeah, I think it's. I remember.
Huh? How do you remember it?
My teacher made that exact point, something like that. Like something goes here. I forgot, but.
Okay.
But something like that.
Yeah, it's something like FBI, and then you shoot FBI, I think. So, yeah, so it should be FBI. Okay. It should be FBI. Okay, so force, magnetic field, and no. F. Okay, I give up. Okay. But what I'm trying to say is, one thing that's clear is that the direction of the force, the outcome of the force, is something that's perpendicular to the plane made by these two vectors. So it's like this. If you have magnetic field and there's a current going like that, then the vector F is perpendicular to this plane. And putting all these together, physicists came up with this new operation among the vectors, and it goes like this. So if you had a W vector, which is U cross V, and this is not a multiplication, it's called a cross product here. Cross product. Maybe I should erase this and say definition of cross product. So if you have a cross product of two vectors, this W satisfies two things. Property one. The magnitude of the cross product is same as the magnitude of the vectors times the sine of the angle between. That sounds a lot like the dot product, right? This is as if it's like the dot product, but instead of cosine, you have sine, right? However, there's an important distinction. There's a property 2. The important distinction between the dot product and the cross product is that the cross product gives you a vector. It's not a scalar. Cross products give you a vector. And the direction of W is perpendicular to both U and V. And the problem is, even with this, it doesn't determine the vector, because let's say this board contains U and V. Let's say you have U and V. Two vectors, U and V. Okay? Now, what's the direction perpendicular to these two vectors? There's one coming out from the board. There's another one going in. Right? Which one do we take? So we have to pick one of the two. So there's a convention, and the convention is determined by the right hand. All right, so let me just talk about right-hand rule, and then that will conclude the definition. So what is the right-hand rule? Well, whenever you take anything apart, or you put something in, you use this right-hand rule, right? Some people call it righty, tighty, lefty-loosey. Yeah, that's what it is. The way I do it is, if I want something to go in, I do this, right? It's going to go in, right? If I want something to come out, I do this, right? It will come out. Whichever direction my thumb is pointing to when I use the right hand, it's the way I do the screws. Okay, so I mean, among all the mathematics I learned from elementary school to my PhD, the most useful math I learned was this right-hand rule when I was learning this cross product. So that's the right-hand rule. Okay, I use it many times. All right. So what that means is this: I have U and V. U, V And the direction of the cross product is here. Thumbs up. And because of the way it's defined, note cross products are only defined in 3D. Okay, you can't define cross products in 2D. Because whenever you have two vectors, the third one will be perpendicular to that plane, so that means you have to be in 3-dimensional space. Okay, let's do a little bit of exercise and then we'll conclude. Okay? A little bit of exercise. What will be I cross J? So let's think about this. All right, so you have X, Y, Z, and your standard unit vectors are I, J, and K, right? Okay, now first determine the direction of I cross J. I cross J gives you, so which direction?
K.
K in Z direction, right? So this is a vector in Z direction. Vector in Z direction, that's definitely true. What's the norm of the I cross J then? This is I times J times sine of angle between, right? But what's the angle between I and J? 90 degrees. What's sine 90? Let's look at the sine graph. That's the sine graph, right? 360, 180. It's 90 degrees. What's the value? 1. Okay. So sine 90 is 1. What's the length of I? Length of J? 1 times 1 times 1, that's 1. Okay. So what is this vector whose length is 1? We know that the magnitude must be 1, and the direction is the z-axis. That's K, right? So we know that I cross J must be K. Okay, now here's an amazing fact. What's J cross I then? It'll be negative K. If you do J cross I, it will be going down. Magnitude is still the same, but it sounds negative K. So this is another very important distinction from dot products. Not only is cross product a vector as opposed to dot product giving you a number, it satisfies the following property. U cross V is not the same as V cross U, but it's a negative V cross U. It's anti-commutative. We just have 1 minute. The last question. What's I cross I?
0.
Yeah. Why? Why is it 0?
Sine of 0 is 0.
Yeah, sine of 0 is 0. So if you do I cross I, it has to be 0 because if you look at the magnitude, the angle between is 0 degrees and sine 0 is 0. So next time I'll actually show you an explicit formula for finding all the cross products.